In this presentation, we're going to talk about grammar error correction for the Ukrainian language. Our research mainly focuses on generating synthetic data for different model architectures, but we will outline a few other things as well. So let's begin. Grammar error correction has been studied extensively for the English language. However, its application to other, less widely spoken languages, such as Ukrainian, remains an open challenge. There are multiple reasons for lack of research on GEC for the Ukrainian language. Cultural context, such as prevalence of Russian over Ukrainian, small amount of resources, meaning that there are much less datasets and language models, significant morphological complexity compared to English, such as the absence of rigid word order, and a lot of exceptions, most of which are not known even to the native speakers. The most logical starting point was to appropriate the methods that are used for grammar correction in the English language. First, these are the two most widely used types of language models. One of them is called sequence tagging. Sequence tagging treats GEC as a tagging classification task, where each tagging word in our case is assigned a label to either keep it as it is, delete it, or replace it. Another one is neural machine translation, where the model must learn to translate from the errorful language to grammatically sound sentences. Moreover, these are the types of synthetic grammar errors that are widely used. We will elaborate on each one further in the presentation. Overall, in the presentation, we are going to tell you about 5 steps that we did. First, we developed sequence tagging and NMT models. Then, we assembled a corpus of clean data and devised algorithms for error creation. Finally, we compared the resulting models via the UNLP shared task. Let's begin with the model architecture.
The first type of models we developed are neural machine translation models. Those models treat GEC task as a translation task from errorful sentence to error-free sentences. This approach requires only a parallel corpus of correct and incorrect sentences to work. For training models with this approach, we use an MBART50 large model fine-tuned on gold corpus with augment data. The average running time for these models was only 15 minutes. Second type of models we developed is sequence tagging models. Sequence tagging models are based on GEC paper for English and the corresponding model. They leverage the fact that not most words in a sentence do not need to be corrected when performing grammatical error correction. Instead, it treats GEC as a sequence tagging task, where we try to classify each token and assign a label with the corresponding edit. To decrease the number of necessary edits, we use G transforms, which combine linguistically similar edits into one. Example of that is transform capital. This transform allows us to combine all the edits that require changing the letter from a small letter to a capital letter into one. This greatly reduces the label space and allows for better classification. For training those models, we use pre-trained XLM or better for Ukrainian language with 2 feed-forward layers on top. The model was fine-tuned on large amounts of synthetic data and then a human-annotated corpus. The average running time for this model took 8 hours on Google Colab A100 GPU, much longer because we needed pre-training on large amounts of synthetic data. Now for the comparison of the models. Neural machine translation models are much easier to develop and train. You simply put in the parallel corpus of data and fine-tune on it, and you get a model for grammatical error correction. They also require less data due to higher quality of open source LLM. The model we used, MBART50 large, is of much higher quality than XLM Roberta for Ukrainians that we used for sequence tagging models. They also, however, require additional functionality to explain corrections. Pure translation models does not have the necessary functionality to interpret corrections and give explanation to end user. On the other hand, sequence tagging models do require a labor-intensive development of custom language G transforms. However, they provide faster inference time and they make it easier to explain corrections to the end user.
So, we need to talk more about synthetic data generation. To train and test our models, we rely on the generation of data. In the following subsections, we explain what technique we use to imitate natural errors for the large corpus of correct sentences. But first of all, determine that we generate 5 types of errors. It's punctuation, grammar, lexic, fluency, and round translation. Let's check them out.
Generating errors in existing sentences, verification, necessitates the existence of a large, mistake-free corpus to verify. To address this, we scraped through a handful of news websites and fiction books we downloaded in agreement with terms and conditions of all the sources. Then, we split the resulting text by sentences. Further, we had to clean the text out of the sentences which would have been unreasonably difficult to tag, such as direct speech. Then, we removed all the auto punctuation and parsing artifacts like emojis. Finally, we standardized the punctuation marks across the entire dataset. As a result, we got a dataset with more than 1 million high-quality sentences. Now we could move on to error generation. The first type is punctuation. You can see the formal definition on the screen. The procedure went as follows. We would take all delimiters between words, treating any punctuation mark or space as such. Then we would run the errorification matrix that you can see down below on each delimiter, generating a new one. The matrix contains probabilities for change from any given delimiter to any other one. For example, we are much more likely to replace a comma with a space than to add a new one. Then we would combine the delimiters together, getting an errorful sentence.
Ukrainian is a morphologically rich language, meaning that words' conjugations will be dependent on gender, on the inflection, on plurality. So, in order to capture at least something, we decided to narrow down our focus only to the agreement of adjectives with nouns. In order to trace such agreements, we make use of MOVA Institute morphosyntactic parsing system. This system makes use of dependency grammar structure. Dependency grammar structures helps us to identify where are the noun phrases heads. So, for example, take a look at the sentence красиво, шелковый тюль. In красиво, шелковый тюль, тюль is of a masculine gender, while both красиво and шелково are put in a feminine gender. So, in order to agree adjectives with an appropriate gender, we make use of Pymorphy library. Pymorphy library helps us to adjust the appropriate conjugations if we pass appropriate parameters.
Now, let's introduce the division of lexic into two subcategories. Starts with Russism. It's a word that has never existed in Ukrainian vocabulary and was just transliterated. You can see step-by-step instruction of Russism generation. Firstly, you check if the word doesn't exist in Ukrainian. If yes, you observe letter patterns in transliterating Russism into Russian, generate each possible way of transliterating, and filter these combinations through Russian vocabulary. And later just translate back. At the bottom of the slide, you can read a formal description of our approach. The second component of lexic is surjik. It's a word that's incorrectly used in the context of sentence, or it's formed by mixture of languages without any agreement. Surjik generation starts with tokenizing a sentence. Later, then translating a sentence from Ukrainian to Russian through the Ukrainian-Russian encoder and transformer. Performing back translating, but using now Ukrainian-Russian instead of Russian-Ukrainian tokenizer as the correct transformer. And finally, just applying a dictionary of frequently misused word forms. It will be more clear in an example. The first table demonstrates us a perfect example of Russified sentence. Look at the English version and let's go through the highlighted phrases. Owner in Ukrainian sounds as vlastnik. So, if you translate it into Russian and apply certain rules of transliteration, we get владелец. Or another word, storks. In Ukrainian calls leleke, but in Russian, aist, using the sound e. But after the same operation, we receive word aist through yi. For surjik, the process performed according to its own algorithm, and we can see incorrect pairs such as reach own agreements and correct ways досягати власних домовленостей. Finally, we can identify what impact to model have different types of data. As you can see in the table, the most significant growth occurs with punctuation data assistance. We are confident that this result is because type of error is one of the most frequent in the test dataset. However, with unit testing, we will see other significant improvement in the results.
Moving towards conclusions, I want to compare the performances of sequence-to-text models, NMT, and rule-based models. So initially, we assumed that rule-based models were expected to help neural net-based models by capturing the errors that neural-based models failed to identify. However, we found out that rule-based models still yield a high rate of false positives. We might speculate that it is due to the fact that the errors that are assumed to be captured by the rule-based layer are quite infrequent. And moreover, the true positives of rule-based models already occur in areas where neural networks already perform well, such as spelling or punctuation. That tells something about results. So NMT-based models already show a better performance compared to rule-based and sequence-to-tag models. The precision of NMT models was notably higher. So we might assume that it is connected to the fact that NMT-based models are making use of byte pair encoding, which captures more nuanced parts of the word, such as prefixes, suffixes, etc. Using a lot of synthetic data or not using a core UA-GEC trained corpus resulted in a significantly worse performance. So it helps us to identify the fact that we might want to make use of a mixed dataset, which makes use of human annotated data and synthetically generated ones. So we augmented the core dataset with under 20,000 synthetic sentences, and that resulted in a best performance.
Our conclusions, first of all, we developed the state-of-the-art model for Ukrainian grammatical correction for the UNLP shared task competition. Secondly, our best performing model was an NMT model trained on human annotated data augmented with punctuation, rhocism, and dilution synthetic data. This showed to us that those three categories of synthetic data are most important or most lacking in the dataset and gives the largest improvement. Finally, NMT models we developed performed much better for Ukrainian by acquiring less data than sequence tagging models. This allowed us to conclude that high-quality synthetic data was more useful than large amounts of data when training grammatical error correction models. Finally, limitations. We did not explore all synthetic data generation techniques, instead focusing on high-quality generation. We did not test all pre-trained transformers due to compute limitations. We did not test models such as MT5, for example. We also used at most 1 million sentences for training, when the SOTA model for English uses at least 9 million. We could also have developed more G transforms for sequence tagging model, as it could be necessary because Ukrainian is a much more morphologically complex language. Finally, we did not test back translation models for error generation, which could provide with other sources of high quality synthetic data. That's it. Thank you so much. If you have any questions, please let us know. We'd be glad to answer them and communicate more about our paper.